Welcome, everybody. Thank you for joining us. As always, please feel free to ask any questions you have along the way if you're watching live. If you think you might like to join us one day, please do get in contact. My details on the channel's About page. Next week, we'll be talking with Andrew Tierney or Cyber Gibbons about IoT and embedded security. But today's guest is Thea Flowers. Hello, Thea.
Hi.
How are you doing?
I am doing great.
Fantastic.
How are you?
Thank you for joining us. Yeah. Oh, I'm okay. Thank you.
Awesome. Glad to be here.
Yeah. So I always like to sort of talk to people about how they got to where they are today and sort of hear about their story and their path. And I'm wondering if you're happy to share us a bit about that.
Yeah, for sure. First let's start with where I'm at.
Yeah.
So I've worn a lot of hats, but at this point in my life, I consider myself a open source advocate and a music technologist.
Okay.
Because I make synthesizers and I make open source synthesizers. But beneath that simple description is just such a world of nonsense. Because what I really am is a swirling vortex of chaos.
Okay.
I got my start like young. I grew up relatively poor, and so I did a lot of reading, and I loved going to the library and reading like old electronics books. And I ended up taking everything apart and learning how they worked and all this stuff. And I got into music at a young age too. And then I got into programming when I was around 12 or 13 because I wanted to make video games.
Okay.
I never made video games.
It's one of those ambitions, isn't it, that many people have.
It's a good ambition because it took me far. It really did. But
Yeah.
I never finished a video game. I learned a lot of interesting things along the way, though.
Okay.
I didn't get a chance to go to college, which is unfortunate, but that's okay. I managed to weasel my way into the software engineering world. I started at a super simple web design firm that did pretty simple websites for small businesses and stuff like that.
You're talking sort of static pages or a bit of dynamic PHP or something in the background?
Yeah, PHP stuff.
Nice.
Yeah, and we had some bigger clients that had some more interesting requirements, but for the most part, things were relatively straightforward. Relatively, right? So I got lucky with that. I was actually in my hometown. I come from a super small town, so I was lucky to even have any company in the town that had programming as an option. But I'd actually never written any PHP before I started that job. So that was an interesting learning experience, coming from C++ and just going straight into PHP.
Yeah.
After that, I got super into Python, and I ended up working at a consultancy for a while. And consultancies are great if you are young and you don't mind spending 80 hours a week working and traveling constantly. Like, I learned a lot, but it cost me a lot. Like, in terms of just like,
your life essence.
Yeah, my life essence. I had to trade a lot of years for that one.
Oh, okay.
Yeah, I mean, it was good though. I got to travel to places I wouldn't travel to otherwise.
Right.
I got to meet a lot of really interesting people, and I got to work on a lot of interesting projects. Right. After that, I moved on to Google. I had been involved with the Python community for a while at that point, and multiple open source projects. And I had the opportunity at Google to do more of that and do more of that on as like my job, which was really cool.
Yeah.
Yeah, like I had a chance to really, take on some of the bigger open source projects in Python. I was the maintainer of Eurolib 3 for a while, which is the most downloaded Python package. It is the underpinning of requests, which is the second most downloaded package.
Yeah.
And one of the most used Python packages. And
very cool.
Yeah, and I get to organize some Python conferences like PyCascades, and that was really fun. I enjoyed interacting with the community. But a couple years ago, I decided it was time for me to move on from Google. I wanted to take some time and just not, especially amid the pandemic and things like that. I wanted to be closer to my family, so I moved back home to Atlanta, and I started getting into hardware. And after doing software for most of my career, it was so nice to get back into hardware.
Okay.
I started with mechanical keyboards, which is a gigantic money pit. I mean, I think if you want to go broke and have a lot of pretty things, like mechanical keyboards is the way to go.
Okay.
But that got me interested in, like, in the mechanical keyboard community, people are really into building their own keyboards.
Yeah.
So not necessarily designing them, but they'll buy like a kit, right, with a PCB, all the switches, and some special keycaps. And people are super into that. And that got me into the idea of maybe designing stuff myself.
Okay.
And I've always loved playing music. I've been a musician most of my life. And I realized I liked tinkering with instruments more than I liked actually playing them. Like, I remember back when I played music in a band, I was the one that like ended up being responsible for maintaining all of our instruments. Like, I'm the one that changed all the strings and made sure everything was set up correctly and made sure all of our amps still work.
Right.
Incidentally, I'm the only one of us who ever had their amp catch on fire. That is unrelated to the fact that I was the one that maintained it.
I promise.
But yeah, so like, as I got into this hardware stuff and I started thinking about synthesizers and music, I was like, this is the thing. This is where this overlaps in such an interesting way that I think it might be able to hold my attention for a while.
Nice. Okay.
So
had you done anything with synths before, or was this kind of the niche that you found to sort of satisfy your crave almost?
So I've been playing around with software instruments for as long as I've been doing music. So guitar is my home instrument. That's what I play the most of. But kind of growing up with not a lot of money, it's like guitar was the only instrument I had too, right? But I had a computer, and software instruments are a lot more accessible to people. And there's a lot of wonderful free ones out there. And that gave me the opportunity to really play around with these virtual instruments and learn about synthesizers and synthesis. So when it came to kind of revisiting that world, and thinking about hardware, it kind of opened up this whole like other part of it where I'm like, oh, there are still hardware synthesizers, like that. There's still a thing. Like software hasn't completely consumed this world, and there are reasons why. And just getting into that and learning like something that you think would just be obsoleted by computers is not obsoleted by computers. And there's so many interesting things going on in the world of music technology. And it was fun. I started messing around with it after I left Google. Oh, I started messing around with it before I left Google, but started getting really into it after I left. And it turned into something that I wanted to do. Awesome. So I started a synthesizer company, and now I sell synthesizers out of my basement.
Well done. That's awesome. Do you make your own music to sort of enjoy it for yourself, or is this something that you put up somewhere, or is it more, as you said earlier, tinkering with the instruments, playing with them, and actually now that you've made them, you might as well sell them? Is that kind of the route you're taking?
So I do actually use the instruments that I make. Like every module I've made with like a purpose, right? Like it's because I wanted
a hole to fill.
Yeah, exactly. The thing is, though, I don't record any music. Like
live or not.
Because like I said, I found out that I was better at tinkering them than playing them. That mostly comes down to writing. I am not the kind of person who writes music. I mean, I probably could if I put my mind to it, but it's just not something that I want to do. Like what I find enjoyable about music, about playing music, is the process of playing it, right? Like it's like doing meditation for meditation's sake, right? It's for me, playing music is a meditative practice because it requires my attention. I can't do something else while I'm playing music. And for me, performing is just that's all I need. All I need is to just play an instrument. It doesn't have to be in front of anybody. It doesn't have to be recorded. Like the joy for me is in the performance. And
I love that. That's really awesome to hear.
Yeah, and I'm happy with that. Like I came to terms with the fact that I wasn't going to write music a long time ago. It's like coming to terms with the fact that I'm never going to make a video game, right? I learned enough to understand how they're put together, and that helps me appreciate them more. And it's kind of the same with music. It's like, oh, okay, awesome. Now that I'm building instruments, I understand that like there's so much that goes into this beyond just songwriting and recording. There's a whole world of instrument makers that go through so much to make things sound nice.
Brilliant. So this is probably a good moment to introduce Winterbloom, your company, and
Yeah.
and the products that you make. Obviously, sort of a big steer towards music and things. Can you just sort of give an outline for the form factor and what it is that they do, generally speaking?
Yeah, so Winterbloom, right now, we sell what's called Eurorack modules. And they're so music is such a big world, and music technology is a big world. And when you start really looking at music technology, you start seeing niches. And then when you look at those niches, you see niches of niches. And so Eurorack is a niche of a niche of a niche.
Okay.
Um, it is it is a modular synthesizer. So most people are probably familiar with a synthesizer, right? It's like, oh, it's like a keyboard, right? You know, you got your things, and it makes sounds, and you can press little buttons and change it between like a piano and an organ and a trombone or something, right? Those are called standalone synthesizers, or monolithic synthesizers. And the reason they're called that is because they're kind of fixed, right? Like you can't rearrange how it generates sound very easily. You can if you crack it open and start doing what's called circuit bending, which is very popular as well.
Yep.
But for the most part, you get what you get, right? Modular synthesizers are the opposite of that. Instead of getting one monolithic thing that's already put together that makes specific noises, you just get the building blocks. It's like Lego. It's like you're building your synthesizer out of Lego bricks. And the way that it works is that you have all of these independent modules, and you can wire them together using little audio cables, right? And some of those audio cables carry audio. Some of them carry control signals. And you can use all of that to change every module and modulate and really shape the way the sound works. And this is what a modular synthesizer looks like. It's a very small one, but it is a modular synthesizer. It's there's a little speaker on this end. This is one of our modules. This is an oscillator. This makes noise basically. This is a filter. This changes the way the noise sounds. And it's such an interesting little form factor. And it's called Eurorack because it was originally designed by this guy in Europe. Yeah, like that's the best explanation I've heard.
That's it.
It was originally called the A100 system. It ended up being called Eurorack. It saw like a resurgence in the early 90s.
Yeah.
And it saw a second resurgence, a couple years ago. And what's so cool is that because like there's sort of a loose standard, is that there are lots of little manufacturers that make these modules, right? There are a few big names, but for the most part, these are boutique shops that are coming up with really interesting designs for modules that can be put together. And because it's like Lego, it's like, it's like if Lego was manufactured by 700 tiny manufacturers that all made unique creative bricks, right? Like it's really cool, and it's an interesting community.
Yeah,
for sure.
Awesome. So Euromodule, I've been aware of it for a while, but I don't know the details of it. So obviously you got those front faces with plugs and knobs and things on it. What else is there to it? Is there like a backplane which provides power and maybe some audio routing, or is it all on the front? You plug your cables in and you get what you get.
Yeah, so almost all of it's on the front. There is a power specification.
Right.
It technically can also carry 2 signals, but almost nobody uses that just because it's so
restricting.
It's not so much restricting. It's just like it just never took off. Like it's part of the original like A100 system, but nobody really used it beyond that. But yeah, so there's like a power specification. It's like a little IDC header, and you get plus and minus 12 volts and ground, and you go from there. So yeah, and then there's basically everything else is on the front, so you get to wire everything together in terms of connecting between modules and putting things together.
And there's some kind of agreed upon like signal levels for the audio, and the control voltages are like within a window, or is it kind of a little bit risky, almost plugging this into that? You might not enjoy it so much.
For the most part, there's not a lot that are risky unless there's like a super poorly designed module. Like all modules that are made from reputable people can handle the full voltage range from negative 12 volts to plus 12 volts. Like it may not respond to that entire range, but if you plug something in that's, in that range, it's not going to fry it, right?
Nice. Okay.
For example, like an oscillator might take a control signal, from 0 to 5 volts, saying this is how high I want the pitch to be, right? With 0 volts being C0 and 1 volt being C1 and so on and so forth. And you can send it a 6 or 7 volt signal, but it's not gonna play anything. Yeah, it's not gonna play anything higher than the 5 volt signal, right? Like,
yeah. Okay.
So that's kind of the idea, is that a lot of these modules will do things like that. And where you start running into sort of some of the differences is like you'll have some modules that will respond all the way up to 6 volts or to 7 volts, or some of them will respond from negative 5 volts to positive 5 volts for some reason. So you'll get weird little things like that, but for the most part, everything works together reasonably well. And for those cases where things kind of have a slightly different range or something like that, there's actually modules specifically for sort of translating between these different levels and stuff like that. So, there's a lot of what we call utility modules to help with that.
Okay.
And even if, even in the universe where everything did respect the same signals for all the different things, those utility modules would still be useful, because sometimes we like to do things that things don't expect. Yeah. You don't always have to send a pitch signal into the pitch input. You can send something really weird into there and see what happens. And that's kind of the adventure that you're signing up for.
Okay, very cool. So in terms of the boards or the modules that you design, then you've got a new one, Micronova, which is a power supply.
Yeah.
Can you talk to us about that? And I'd love to hear about things like, from the conception through to design ready and complete, and then even onto production and shipping and making it available for people to buy.
Yeah, so there's a lot there, and
I know.
Feel free to stop me at any point and be like, hey, tell me more about that.
Yeah.
So Micronova is another one of those things where like I wanted it to exist. And so this little case is actually an example of where I wanted it to exist, because this is a tiny, adorable case, and I wanted a tiny, adorable power supply to go with it. Because this is a very small modular case. Like it only fits a handful of modules. Most are what's called 84 HP. HP stands for horizontal pitch. So that's about this big.
Okay.
This is much bigger.
We're kind of looking at 19-inch rack type size, are we?
It's literally a 19-inch rack.
Oh, okay.
Yeah.
Okay.
So
nice.
There you go. And yeah, so I want a little case, and the big cases have big power supplies and stuff like that, and they're expensive, and they're not really optimized for this use case. And what I really wanted to make was a power supply that was kind of like a love letter to the DIY people who are making tiny little cases like this. And so this is actually Micronova right here at the bottom. It sits inside the case. This is what the board looks like without all the through-hole components on it. So it's missing. It's missing the through-hole bits, but that's the board. It is very small. It is like 100 millimeters by 30 millimeters, I think.
Nice.
I dropped it. Oh wow. It is about as small as it can be. And it's great. So the concept here was to make a small but very efficient and useful power supply. And so there's a lot of things on here that I put on here as kind of affordances to DIY people, right? One of the things is that because of the way that it's done, you don't have you have multiple ways of giving this upstream power, because you have to plug it into like a DC wall wart or something, right? And there's these two little barrel jacks on the back. Those are optional. You can leave those off if you want to. There's also this front panel thing that has two DC barrel jacks and a switch. If you wanted to put a switch on there. So if you didn't want to cut a hole in your case and you just wanted to have it on the front, you could do that.
Okay.
There's also,
so the two barrel jacks, are they in and out or for chaining, or is it generally like two 9-volt supplies then get?
No, we're not doing anything hacky like that.
Okay.
It takes a 15-volt supply and it does the rest from there. And those are for daisy. Those two are for daisy chaining. So The idea is that if you have more modules than you can reasonably power with one Micronova, you could actually chain multiple ones, either within the same case or within multiple cases if you wanted to.
Okay.
So that's another one of the affordances, is that, you know, if you do need slightly more power than just one, you can still stick with this, right? Like that's kind of the idea.
Okay.
Yeah, yeah. And so, you know, there's all these kinds of neat affordances like that. And yeah, I mean, for me, I just love it. It just gives me so many options when I want to put something together. Um, and I don't know, I like it.
Okay.
It also came out of the need, like I wanted a power supply for our test setup that we use to actually test our modules. That wasn't my bench supply, because it is a little bit of a pain in the butt to connect it to the modules.
Right.
And also I sometimes want to use it for other things. So yeah, this, and there's actually like a prototype version of this that's literally just taped inside of our test rig setup.
Nice.
And it's been running flawlessly for like 4 months. And it's absolutely a prototype, right? Like like none of the components are in spec for what they should be, but it's still just chugging along. And
yeah,
you know, that's wonderful.
awesome.
But yeah, so that's kind of the idea. You know, the idea was that small but useful, you know, like a lot of useful features. And I also wanted it to be relatively mighty, as they put it. Like I call it tiny but mighty. The thing with Eurorack modules is that every single one of them will consume a different amount of current. So they each have a different amount of like power demand on your power supply. And you have to be careful when you're putting together your system, because you have to pay attention to how much you're drawing from your power supply, because you can very easily go over that, and then all kinds of weird stuff is going to happen. So you know,
I'd imagine that a lot of them are not static power draw as well. It's quite dynamic, but based on what they're doing, maybe.
Yeah, exactly. You know,
so it might work in one configuration, then you use it another day, and all of a sudden it's behaving weirdly.
Yeah, exactly. And you know, for the most part, manufacturers do put the max power draw as their rating.
Yeah.
And there's a really useful site called Modular Grid where you can virtually build your rack, and it will tell you how much power it's supposed to draw, which is really great.
Okay.
But yeah, so like, you know, people have to be careful about that. And I wanted to make sure that this would be able to supply an entire small case like this and then some. So you know, I had to be very choosy with like during the design phase with like what parts I chose to be able to actually fulfill that requirement while also keeping it small.
Yeah.
And you know, I think what really kind of made this design possible and feasible was these DC to DC converters, like fully integrated DC to DC converter components that have started becoming a lot more popular in recent years. And they kind of started with these like little replacements for the old school 7805 style regulators, the big, you know, TO whatever things, big chunky boys.
220, yeah, that kind of thing.
Yeah. And like they were like drop-in replacements, like replace your, you know, inefficient, you know, heat generating linear regulator with, you know, a DC-DC converter that's using, you know, a buck or a switching regulator, and, you know, reap the benefits of, you know, less power usage and stuff like that.
Yeah.
And that's awesome. But through that, they also started coming up with, you know, different form factors that make a lot more sense. And one of those form factors is this tiny little black box that you see on this board, right? Look how little it is. Nice. So that is a fully integrated DC-DC converter.
Wow.
And
no extra components to support it at all. That is it.
Exactly. All you need, and they're optional, are 2 capacitors, one on the in, one on the out. You don't even actually need them. The one on the input is just recommended if you're far away from the upstream power supply. The one on the output is only recommended if you are, if you have like high dynamic loads.
Right.
So if you're like using doing a digital module or something like that has a pretty constant load, you don't need them.
Okay. Nice.
Yeah. So they're great, and and like they have like an absurd input range, like 0 to 36 volts or something like that. And what's amazing is like this little bitty black box can supply 500 milliamps of current. It can do half an amp in a tiny black box. And there's also ones that are the same size. Actually, they're slightly bigger, like 1 millimeter bigger in one dimension. They can do an entire amp. So because of these, I was able to design a power supply that's this itty bitty with 3 rails. So it has 12 volts, negative 12 volts, and 5 volts.
Okay.
And it can provide 1 amp on the 12 volt rail and half an amp on the 5 volt rail.
Nice.
That is amazing, right?
Yeah.
Like, you know, and from a design and cost perspective, I don't have to design 3 separate buck regulators for that, right? Or, you know, 2 buck regulators and 1, you know, inverting buck boost or something like that, right? With all the component complexity that comes with that, all the EMC stuff that happens, because, you know, this is also designed with EMC in mind. So it deals well with noise, it deals well with efficiency. Like, they're honestly incredible little products. And
nice.
Yeah, so that's kind of the one component that really enabled this design to happen, right? And I think that's really cool. And the rest is, you know, sort of just doing the right thing, right? Like making a well-engineered system. So there's things like reverse polarity protection. There's a polyfuse in case there is a dead short on one of the output rails. Although the DC-DC converters actually do also have overcurrent protection.
Nice.
So really that fuse is there if for some reason those fail catastrophically and
extra safe.
short.
Yeah.
Awesome. So it is very rare that that would happen. There's also a Serra diode or a metal oxide varistor for transient voltage suppression, which is useful for when you're unplugging and plugging in things. There's LEDs to help you figure out if everything's working okay. You know, and there's noise filters. There's filters for both, you know, keeping noise out and keeping it from emitting more noise itself. So if you have analog modules downstream, it's not going to bleed into them.
That's a big thing, isn't it? Especially with audio, because it's so noticeable when there's audio frequency noise in your system. You know,
especially with older buck generators, because they operate at such a low frequency that it can easily cross over into, you know, the frequencies for audio, and that is a nightmare. And even with these newer higher frequency ones, if you're not really careful about your design, you can actually end up causing reflective noise to couple into the audio range, and what a nightmare. So I think these little DC-DC converters are amazing.
Awesome.
Yeah, it's not that I didn't have to worry about that stuff, it's that I don't have to worry about it as much.
Okay.
Cool. And you asked
so
about,
how does obviously the design side of things, using a brick like that, you just plonk it down and off it goes, pretty much. If you had to design the power supplies yourself, then obviously there's much more considerations, design, whatever that goes into it. So the cost side of things for your BOM and your product, is that kind of a justification, or is that like it's a low volume thing, therefore I'm not going to be putting loads of time into making it cheaper? You know, how do you stand on that side of things?
Yeah, I mean, so that's such an interesting question, especially with something like these DC-DC converters, because part of their value proposition is reduced BOM count, not necessarily reduced BOM cost, but in the world that we live in right now, reduced BOM count is actually like really valuable. So, you know, for me, looking at it from a design complexity perspective, you know, sort of like the cost of having more complexity in the design was higher than the cost of putting these on there. So like with that, it's kind of like, it makes sense, you know. And you know, having the overcurrent, the over temperature protection and things like that are so valuable for something that has to sit between, you know, electricity and hundreds, if not thousands of dollars worth of audio equipment, right? It's not a place where you want to start cutting corners when you start putting in your own buck regulator that you design, and you're like, oh, you know, I'll use lower value components, or I'll skip this filter. You know, I don't need 17 caps on the end of it, all this shit, you know, like, it's like, you know, you don't have to worry about that. You don't have to worry about, you know, reducing all your components to the absolute minimum to try to shave off cost when you accept the fact that this is going to cost money because it has protection.
Yeah.
It has features, it's efficient. Like these things are up to 98% efficient.
Oh, it's crazy, isn't it?
And if I was going to do that with a discrete design, like, oh my God, I don't even want to think about it. Like, it would also be a 4-layer board, at least a 4-layer board. Like, no thanks.
Very cool. I've just realized we've been talking for half an hour already. We've got so much more to talk about. So let's move on.
Absolutely. Let's do that.
You mentioned that you moved earlier, and you're sitting in your new workshop. So can you just really quickly talk about how that was to set up a new workspace and get your stuff going again?
Yeah, moving was really interesting. So I bought my first house.
Well done, congrats.
Right, like such a rare millennial thing to do,
Yeah.
to buy a house. So I live in Atlanta, and there's a lot of lovely options in Atlanta for houses, and this was the first one I toured, which was really surprising because I toured.
No way.
Yeah, I toured quite a few.
Okay.
But this one was just so charming, and it had this basement, like walkout basement set up. That's kind of like, I guess kind of set up to be like an in-law suite or something. Because it has like a living room down here, and it has a den, and it has like a bedroom and a bathroom, and it has a nice like deck off the back. So yeah, I'm like, this is a great space for me to set up shop in, right? Like, I can make the living room my workshop. I can make the bedroom the music room. I can, use the den for other stuff. And those were all great ideas.
Oh.
But so moving in, I ended up having to do a lot of work because this basement had carpet in it.
Okay.
Like 16-year-old carpet that wasn't great to begin with. So all that had to go. Oh my God, what a nightmare. So I had to rip up all the carpet. So the floor underneath is concrete, so I had to like, scrape all the carpet glue off of it, and then like re-level it and all this stuff, and then put in the flooring myself. So I did all that myself with some help from my sister, and that took forever. But then I finally got a chance to start setting up my shop, and it was so exciting. And I was actually working out of my bedroom before then. So like literally everything that I used to build all these things was just in my bedroom. It was a nightmare. And I actually have the opposite. I have the opposite problem now, where my bedroom upstairs is completely empty because all the things that used to be in it are down here now.
Is it too far away as well?
Yeah, it's I have this big empty bedroom now with nothing but a bed in it. I'm like, this is like, peak college male living space up here. That's, in the basement, it's amazing.
Nice.
Yeah, like really just, getting these big, work surfaces that you see here in the back, and getting the pegboard set up, and getting some shelves hung, and, really giving myself a lot of like room to organize and all this stuff. Also, there were these built-in bookshelves next to this fireplace. I have a fireplace in my workshop. That's a little flex for y'all. It had built-in bookshelves, and I actually ended up adding a few more shelves to it, and setting up my 3D printer stuff right there. So this nice, organized little area for 3D printing, which I think is really cool.
Very cool, yeah, nice.
And so there's another worktop that's just like this one on the other side, and we use that for packing and shipping orders. And there's a table right here in the middle, which is what I'm at right now, that is currently home to me and this pick and place machine.
Ooh.
Yeah. So
very good. So that leads us very nicely then onto the work you've been doing with the pick and place machine.
Yeah. What would you like to know?
I would.
there's a lot to say about the pick and place machine. So I've been working on this pick and place machine. It's open source. It's called the Lumen PNP. It's by Stephen Hawes, who has a great YouTube channel where he talks through the whole process he went through with designing this thing. He's still releasing videos because he's working on feeders for it. He's just such an enthusiastic guy. I genuinely love like watching his videos, and now that I'm helping out the Lumen folks with documentation, like I get to chat with him like every other week when we kind of like do like an informal meeting between the people who are contributing to Lumen. And he's always so excited about something, and that's infectious. I love that.
Yeah.
But yeah, so I got the Lumen, I put it together, and then I did the thing that I always do where I'm like, I want to change things. So I started changing things, and then I broke things. I'm like, I'm going to design my own thing for this. And here we are a couple months later.
So before we get into the now, what was it you broke? And it is, how did it go? What went wrong, and why did you end up in your current situation?
Well, okay. So I broke things because I just like to mess with stuff.
Mm-hmm.
So one of the first things I did with it was like, I want it to be faster. So I put it had V rollers like the Ender 3 printers have for like moving the X and Y axis. I swapped them for linear rails, which are so much better. So like, I want this to be faster. So yeah, I put linear rails on it, and it started running into the limitations of the control board and the motor controllers that were on that. Ended up frying one of my motor controllers on the control board. Yeah. And then later I fried the STM on the control board through some unfortunate circumstances. Certainly not me plugging in something to the wrong port or something.
Of course
not. Nothing I would do, not me, a professional. But also like it has this what was called like an umbilical. The V3 has actually a cable chain, but there's like this whole mess of wires that goes from the bottom of the machine to the head of the machine, where the actual like things to pick up items and put them down are. Because there's a lot of motors up there. There's motors to turn the nozzle so we can rotate the part. There's motors to like move the nozzle up and down, and all that jazz. So there's like an end stop on it as well. And I'm like, I don't like this mess of wires. I want this to be neat and tidy. So that sort of ended up with me starting to design my own controller for the head of the machine. And because I broke my controller for the rest of the machine, that ended up with me designing my own controller for the rest of the machine.
Oh, never mind. Let me put one there as well.
So it's actually starting to become a bit of a joke with the Lumen team that like whenever like they're like, oh, we need to design a new board. Someone's like, oh, Thea's already finished it before we finished the meeting, before we finished the sentence. And it's just like, help.
Nice. So what are these new boards that you've done?
Oh, these are so cool.
I'd love to see them. Yeah.
So I'm going to start with the controller for the rest of the machine because it's the simpler one. I guess it's the simpler one in terms of like it's all on one board and not doing really weird things, which I'll get into. But this is the one for the rest of the machine, and this controls the X and Y axis of the machine down here. So these are 3 TMC 2209 motor controllers, the same ones that are in the Prusa Mini. They're very nice motor controllers for so many reasons, but they also have sensorless homings, so I don't have to do in stops. I can use the chip and some of the feedback mechanisms in it to actually find home by itself, which is great.
Awesome. How does that work? Is that sort of bump it into the end and it will figure out the current, torque, whatever, and
yeah, it's really interesting. So the way that it works is it measures the back EMF from the motor. And basically that increases as the motor is under more load. So you can kind of think of the back EMF as sort of like the inertia, the resistance of the load, right? So the more torque the motor is trying to put out, the higher that's going to be. And what's really great is that for a specific motor and a specific speed, you should have a specific back EMF reading. So if you take your axis and run it at that speed towards the end stop, the physical end stop, not some switch, right? As soon as it hits that end stop, that reading of back EMF is going to change. And as soon as it does, that's home. So that's how you know it. And it's so cool that this chip has that integrated, like the ability to measure that back EMF force.
Yeah.
And EMF force. It's already a force. Yeah, so like it's really neat that it has that, and it's not perfect. It doesn't work across the entire range of the motor's velocity or the motor's
Okay.
torque, which is why you have to do the homing at a specific speed that you kind of calibrate for it.
I see. Right.
Which is why if you use a Prusa Mini and you tell it to home, it's always going to home at its own speed, like even if you set it to something else in G code.
Right.
Because it has to, because that's how it's going to find home with those motor controllers.
And so when you say it's homing at its own speed, presumably that's quite a low speed so that you don't get the mechanical and physical inertia involved, or?
Actually, no. So it can't be too slow, because if it's too slow, like the EMF will actually be, the back EMF will be higher because the motor's working at lower powers because of the chopper is basically sending out like shorter pulses. So it actually kind of looks like the motor's working harder when it's going slower.
Okay.
And when it's going faster, because it's already got some momentum, and because the motor controller is putting more current into the motor, you actually get a better range, like a better reading when you're like in between like a certain set of speeds between minimum speed and maximum speed.
Okay.
So you can't just like slowly accelerate and hope it works. Like that's not going to happen. You do have to like make sure you hit that one speed before you go on bumper.
Yeah, is it scary watching at home, knowing that there's no mechanical whatever's? I don't know. I feel like it would be a little bit.
It was less scary when I was doing it with Marlin. It's more scary when I was implementing it in my own firmware because I messed that up a couple times. And
right.
I have I have a solution to that, which is this big button right here.
Nice.
So when things go wrong, I just smack the button and it cuts power, and then I can try again.
Awesome.
I recommend this for anybody who has a machine that moves around under its own accord. Yeah. So, so it's got these motor controllers. It has controllers for two vacuum pumps, because the way that the nozzle works is that it's a vacuum nozzle to pick up the tiny little parts. So it has two little controllers, two MOSFETs for turning on and off the vacuum pump. It has two smart controllers to control solenoids to open and close those valves that control the vacuum nozzles. So you can pick up and release a part. Yeah.
Is that positive and negative pressure kind of thing?
It could be, but it's not. It's an open and close sort of thing.
Right.
And at the top here, it has two spots for vacuum sensors. Those actually just arrived. I haven't put them on the board yet.
Nice.
So there's vacuum sensors so that you can actually use the vacuum pressure that the sensors read to determine whether or not you successfully picked up a part.
That's awesome.
Yeah, because once you pick it up, the pressure is going to drop. So so that's super cool. So it's got those vacuum sensors on it. And then, over here on the other side, it's got some sort of peripheral stuff for controlling some LEDs around the bottom camera. And it's got an RS485 interface for talking to the feeders when those happen. It's pretty neat little board. And it's got an RP2040 as the brain.
Nice. Okay.
Yeah.
I was going to ask.
The only chip you can get your hands on right now.
Yes.
So. Also, it's nice. I've been enjoying working with it because I've been writing my firmware from scratch here.
Yeah. Cool.
So that board is cool, but this board is cooler.
Okay, tell us.
This board is cursed.
Oh, don't say that.
So on this board, there's a nice USB-B connector, nice mechanically sound connector. On this board, there is no such thing. So how do we talk to this board? Well, there's a footprint here, and I haven't actually filled it in yet with the actual part. But I don't know if y'all can see this. It says not Ethernet. This is where a Cat6 cable goes to an 8P8C connector. Some people call it an RJ45, but it's an Ethernet jack basically.
Yep.
And on that Ethernet jack and on that Cat6 cable, I'm actually sending two USB differential pairs. Okay. One for this board, one to talk to the controller on this board, and the other one for the camera that's on the top of the controller.
Right.
I'm sending 24 volts power for this board, and the motor controllers on it.
Yeah.
And yeah.
That's exciting, maybe.
I think it's truly absurd.
Yeah. So
And
I'm delighted that you've got USB going through them. I was almost not expecting that to work.
so there's a reason it works. So I was going to show
Oh,
the
okay.
board. This is the board that sends all the signals through.
Okay.
So there's the Ethernet side or the Cat6 side, and then these are 3 USB ports. One of them is actually just a pass through to a connector on this board for the bottom camera because it has
Okay.
a weird USB connector. But so you can kind of ignore that part. But yeah,
Mhm.
here's the 2 USB connectors for the camera and the board, and then there's the Ethernet, and then here's where 24 volts goes in to also pass
Nice.
along to the headboard. Um, so the thing is that Cat6 and even Cat5 is shielded twisted pair. USB cables are shielded twisted pair.
Yeah.
Twisted pair is twisted pair. And the thing is like as long as that Ethernet cable, as long as the Cat6 or whatever, like satisfies the USB spec for a cable,
Yeah.
it's gonna work.
See, I thought, I may be misremembering, so please correct me, but I thought Ethernet was 100 ohms differential and USB was 90.
So,
but maybe it doesn't matter enough that
it's not that picky. Like
happy enough. Yeah. Okay.
Yeah, a difference of 10 ohms is nothing. Like
nice.
That's the difference between like a 1 foot USB cable and a 3 foot USB cable, right? Like it's really not that big of a deal. And generally you're gonna run into way more issues with board impedance before you run into issues with that, like a twisted pair. But yeah, it's perfectly happy running over. I wouldn't try to run USB 3 over this, especially with power also being on the same cable. Like you could probably run USB 3 over an Ethernet cable if that's the only thing on that cable. But in this case, one of these is a full speed device, one of these is a high speed device. So it's fine.
Nice. Very cool.
Yeah, so it works fine. Sending 24 volts over it is actually totally fine as well because you don't get a lot of resistive losses at that voltage.
And are you using 2 pairs or something? So you've got the positive on one pair and the negative on the next pair?
It's actually there's 2 pairs and one wire in each pair carries power, one wire in each pair carries ground. But yeah, this is also just because of the way the Ethernet cable is laid out when you actually break it out. It's like inner pair, and then another inner set with pairs, and then there's 2 pairs on the outside that are it's weird. It's easy to mess up. I messed it up twice. Right? But yeah, so power over Ethernet uses like up to like 48 volts or something. Yeah. So, there's a reason that it uses a high voltage to reduce resistive losses of distances, just like, with AC. So yeah, everything works surprisingly well. And the thing is, as cursed as this is actually totally commonplace in industrial environments where industrial Ethernet or, Cat6 is used a lot to connect PLCs together and their accessories. So this is... While it seems so cursed to those of us who do, this stuff as a hobby, and to anybody who's ever read the USB spec, it's actually totally normal.
Surprisingly common, yeah. I know that things like RS485 often put through Cat5 cables and Anyway.
So
very cool.
It's cool stuff.
So the first board you showed us was the Starfish, is that right?
Yeah,
and that's the main control board, and then the second
Starfish.
And the second pair were Jellyfish?
This is Jellyfish, yeah.
Nice.
The Jellyfish on the back. Yeah, so both of them are similar in that they have, they have 3 motor controllers that are TMC 2209s. They're both controlled by a Raspberry Pi Pico. They use almost the exact same circuit for stepping down the 24 volt power to, the power needed by the Raspberry Pi and such. Yeah, so there's a lot of similarities between the two. It's really just that this one has a weird form factor, and the other one has, controls for the vacuum pumps and stuff.
Right.
So.
Okay.
Yeah.
Brilliant. So if you are willing to hold up the back of one of those boards again, you've got awesome little creatures on there, and that leads us really nicely onto our next topic, which is gingerbread. And putting art on PCBs, I think, is a fair way of describing it.
Yeah.
Please correct me.
Yeah, so both in these boards and especially in the boards that I would make for Winter Bloom, we deal with PCB as an art form.
Yep.
And one of the things that you like might not be readily apparent to people just looking at this, these panels, all of these front panels are PCBs. They are made of FR4. So it is like, I'm going to take this now. This is actual fiberglass. It's a regular PCB board. It's just not used electrically. It's used aesthetically.
Yeah, and it makes so much sense because they're cheap. Having a PCB made is you get holes in the right places, you get silkscreen, you get all of this stuff effectively for free.
Yeah, and if you can work within the limitations of it, like you can achieve some really incredible results.
Yeah.
And yeah, like I already have to get a PCB manufactured anyway. So yeah, ordering some more just to use as the front panel is fantastic.
Yeah.
So this is hard to do. It's hard to do both from a design perspective. You're working with some real limitations, right?
Can I pause you real quick? Sorry.
Yeah.
We just had a question in from Southpaw Shorts asking about G-code and 2 separate brains.
Yeah, that's such a great question.
Yeah.
So there's firmware out there like Clipper, which inherently supports multiple boards.
Okay.
So you can use Clipper, and there's Clipper support for the RK2040. In this case, I'm actually writing my own firmware for them because I love to suffer, or I guess, I don't know, God has cursed me for my hubris, and now my work is never finished. So in this case, each one of them is an independent control board. But the software that's running the pick and plays OpenPMP supports controlling multiple boards as well. So so OpenPMP can deal with having basically a split brain.
Nice. And so the computer's effectively talking to the 2 boards and its own links, and there's no sort of daisy chaining or anything like that going on.
Nope.
Yeah,
nope.
awesome.
They're totally independent. And Clipper also works fine that way. Like that's sort of what Clipper expects. When Clipper was being developed, these much more wild and crazy 3D printers were coming up where they had like 4 motors for the Z-axis. So you needed to string together multiple boards just to be able to run the thing. Because there were no control boards with 8 motor controllers on them or anything like that yet. There are now, but yeah. So like what Clipper does is it has like a virtual serial device, and then Clipper itself talks to the boards, the firmware running on the boards to, sort of.
And that kind of acts like a router almost, does it? And
and
forwards the messages where they need to go.
And it coordinates and everything. And OpenPMP is kind of similar in that way.
Okay.
Yeah.
Nice. Thank you very much.
Fantastic question.
Yeah, thank you for asking. So back to Gingerbread and art on PCBs.
Yes.
This is a fascinating topic. We spoke with Bleep Track the other day, Sabine, and I'm sure you've got your own things to say on this topic. And I know you've got your own things. I'd love to hear them.
Yeah. So, it's like I said, it's hard from a design perspective because you're working with limitations. You have basically, whatever color you choose for the solder mask, which in our case is black. You have gold, and you have white for the silk screen, or, if you choose a different color, black, I guess. And you have exposed FR4, which is kind of yellowish. And you can also shine an LED from the back and light it up, which is something we do a lot of because it's a very cool looking effect.
I'm not sure I've seen them, but yeah, carry on.
So, you have to design within those things. So just in terms of thinking of art and making something that's legible for a front panel, you kind of have to think about that. It's not the end of the world. You can make super simple front panels that are just 2 colors, People do that all the time. No shame in that. But for us, we wanted them to be artistic and pretty, and it's very important to do that. The other challenge is that when you're working in a design program, you're not necessarily working in the physical realm, right? Your design program is not made to really match up with mechanical interfacing. So for us, because we're making front panels, we have to make sure that holes are in certain locations so that, our, knobs and our jacks and everything can poke through. And we have to make sure that the board outline is the right size and the mounting holes are in the right position. Because if they're not, if they somehow get lost between our design program or somehow get mutated between our design program and sending it off to the manufacturer to manufacture as a PCB, then that's going to mess everything up, and we're going to waste hundreds, if not thousands of dollars on a run of boards that don't work. So that's hard, and there are tools out there to help with translating vector art, like from Illustrator or Affinity Designer or Inkscape into KiCad. And there are some that are great. Like SVG to Shenzhen is probably the most popular one. It is a fantastic piece of software that is unfortunately tied to Inkscape, and Inkscape does not work for me. I love Inkscape. I love that it exists. I'm happy that people work on it and use it and love it. It is not for me. I can't do it.
Fair enough.
And like, that's okay. I want so much to love it, but I just can't, like there's a lot of things like that out there in the tech world that I'm like, I just want to love you, but I can't. So I tried and failed with SVG to Shenzhen, especially when it came to mechanical, like keeping the mechanical properties the same as I, moved it from program to program. Because in my case, I had to move it from Affinity Designer, which is where I actually do my designs, into Inkscape, and then from Inkscape into KiCad. And each of those steps took so long, it was basically impossible to iterate.
Right. And your confidence in getting the right thing through was low, I guess, as well.
Exactly. Okay. So,
can you talk to us quickly about what sort of thing goes wrong in each conversion step, or can go wrong?
Yeah. And I mean, this is still a concern with the tools that I've made. So one of the things is like SVG is a unitless format. So, when you're exporting between these vector design tools and other tools, you're generally going to be working with SVG, because that's, other than like PostScript, it's really like the only really portable vector format that we have right now. And SVG is unitless. Like your design program may say, oh yeah, we got 72 dots per inch. So it's, this many inches, about that many inches or millimeters or whatever. And that's all great in that program. But as soon as something else opens it, it's like, I don't know what this is.
Okay.
And so,
and there's no like meta anything to describe how to interpret the SVG in the real world effectively.
I mean, there can be, but it's often program specific. So,
and okay, separate.
Yeah. And so, you run into things like that, and also just layers don't always come across the same way. There are times when programs will use extensions to the SVG standard that Inkscape is just like, what the heck? Why did you do this? And it works fine in a browser or something. And you're like, well, Chrome can display it, Firefox can display it, Inkscape hates it. Great.
Now what? Okay.
But also SVG has transformations, and the thing is that, so like literally matrix transformations, so full on affine, transformations, and all of these things combined together with the fact that almost everything that deals with SVGs deals with it in floating point. And because you have like, okay, you're exporting it at this DPI, and you can tell the next program that you're importing it into that it's that DPI, and you'll get the right size, hopefully. But it's also going to recompute all those like, scaling and transformation matrices and stuff like that. And those floating point errors accumulate. And they accumulate in a way that makes you want to rip your freaking hair out. And, for things like making sure that things are mechanically correct, it's a nightmare, because you can end up with things off by 0.1 millimeter. And 0.1 millimeter is sometimes enough to mess up your world. And you can sometimes end up being off by a lot more. And you can also end up just being frustrated by trying to translate DPI between each program. So like, there's so much that comes up. And, SVG to Shenzhen solves some of these problems really well. Like KiCad's format is a vector format, but it's a very limited one, right? So SVG to Shenzhen actually does a really clever thing, which is also what Gingerbread does, where it rasterizes each layer that is going to go into KiCad and then retraces it. It sounds absurd, But the
Yeah.
thing is that it's so non-trivial to translate all the different SVG things into a much simpler format just because of all of the nonsense around it.
That's
That
amazing.
it
Okay.
is actually easier in this case, in the case of where we're going to something that has literally 4 colors to
Yeah.
work with, like, your layer is a binary on or off, right? Like, to just render it to a black and white image, apply a threshold, retrace the outline, and send that in. And that works surprisingly well. It's incredibly effective for something that you think would not be the way that you'd want to do it. But
Yeah.
like I said, SVG is a nightmare. It really is. It's
Okay.
the only thing we have. It's the worst possible option except all others. So
There you go.
it's clever. So both Gingerbread and SVG Shinzen handled translating those graphic layers in that way.
Okay.
Where Gingerbread really differs is how it handles the outline of the board and any sort of internal cutouts. Also, it differs from SVG Shinzen in that Gingerbread is a standalone thing that does not depend on Inkscape at all. It's currently a Python script. I'm working on porting it to WebAssembly so it can run in the browser, so nobody has to install anything.
Very cool.
Which is super cool. Yeah, so what Gingerbread does for the board outline is that it does actually do that SVG translation from, the SVG path specification into real coordinates. And
without that rasterized step, or with it?
Without the rasterization step.
Okay.
Because the thing is, when you're talking about graphics, right, we're not generally super worried about being totally accurate to the mechanical specifications of the original artwork, right?
Yeah.
Like I don't care if my my text is slightly larger or something. What I do care about is if my holes are in the wrong place. And yeah, so what Gingerbread does is when it reads an SVG file, it loads all of the coordinates in that SVG file into a fixed point representation, so that it can do accurate math on them as it translates between DPIs and applies transformations.
Okay.
And it goes through and looks at all the circles that are on the drill layer, and it translates those into drills, maintaining the location. It looks at the outline layer, and the outline layer has to just be a path. It can't be anything else, right? It can have holes in it, so you can have cutouts. In the end, it just needs to be a path. And so it goes through that path and translates that into KiCad format using, again, fixed point math, doing the transformations, making sure that it actually maintains this, this thing to the step. And through this, I also found an interesting hack, which is where you set your DPI to a multiple of 2.54, which is how many millimeters are in an inch, right? So if you export your SVG at a DPI of 2,540, all of the floating point errors will be beyond the point where you care about them. So since the math that I'm doing in Gingerbread guarantees that the real part of the number is always going to be correct, when it loads in, it eliminates an entire class of bugs, right? It's awesome that that's a thing that can be figured out, because it's surprisingly effective. It's just like the rasterization stuff, right? It's okay, that's weird, but given the world that we live in, it's amazing, right? It works.
It does the job. That's the main thing, isn't it?
Yeah. Very cool. So Gingerbread is a really cool tool for me because it takes the iteration time that I used to have to deal with for designing boards from days to minutes. And it takes the iteration time for me to take a design from Affinity and see it in KiCad. It takes that to 10 seconds.
That's awesome.
Yeah,
well done.
Yeah, it is a game changer for me, and I definitely want to make this useful for other people. And I reached out to Carrie at Alpenglow Industries, who does some really interesting PCB art stuff for their kits, and they sent over some of their designs, and it was so cool to do this with someone else's designs, especially ones that have weird board shapes, because I found so many bugs. It was great.
Oh, brilliant.
Yeah, and it's delightful, and I'm hoping that other people will find this useful eventually. And I had some people try it out and everything like that, and where they started running into problems is installing it. It's written in Python, which for the most part can work pretty well if people are familiar with Python. The problem that happens is that it uses some native libraries. So on Windows, it needs a compiler, right? Like you end up having to use something like W to make it easier to use, and that's a lot, right? Like having someone deal with this huge rigmarole of like going through and installing all this stuff, especially if they're not a programmer, and a lot of people who are doing PCB art are not programmers. It's a nightmare. So what I'm trying to do now to really kind of take this core experience that I have that works well for me and get it to a point where it works extremely well for others. And I'm going to translate it to WebAssembly and get it working in a browser, so you can literally drag and drop your SVG from Illustrator or Affinity or Inkscape into it. You can change all the settings that you might want to change. You'll get an instant preview of what it will look like in KiCad before you even hit the export button. And
so good.
Yeah, and it'll take it from there. And
awesome.
I actually spent the last week or so experimenting with how that might work.
Nice.
And I actually got the core of the whole process working. I got it compiled to WebAssembly using Zig. Zig is a new programming language that has really great cross compilation stuff. And it's also a C compiler. So I was able to compile these C libraries that I depend on in Python behind the scenes. I was able to just compile those to WebAssembly, and then sort of port some of the Python code that was orchestrating those to Zig, and then expose all of that to WebAssembly. And I actually got that working to where you can drag a single image and it will give you a KiCad footprint from that image.
So good.
Like immediately. I think I gave it like a 10,000 by 10,000 pixel picture, and it gave me a footprint back in 42 milliseconds.
Oh, that's awesome. So good. Another question from Southpaw. Will this work with Illustrator as well?
Eventually, yes. I don't have Illustrator right now.
Okay.
I don't want to pay Adobe. Hold on.
Hope you're okay. Yeah.
I'm just talking too much.
Sorry.
It's okay. It will eventually.
Eventually, yes.
Yeah.
Awesome.
I just don't have a copy of it right now, and I want to get everything else working. But there's no reason why it shouldn't work for Illustrator.
Nice. Thank you very much. Thank you, Southpaw.
A great question.
So I think now I'm conscious that you need to stop in a minute, but I'd hoped to spend a little bit more time on this, but we'll squeeze it right in the end there. Is documentation, communication, all that kind of stuff.
I feel so bad because this is what you really wanted to talk about.
No, it's not what I really wanted to. I mean, I've loved talking to you about everything else as well. So, you do a lot of documentation. It's fantastic. It looks really good. It's interactive in some cases. Can you just talk to us about your sort of your approach and what your thoughts are going into that kind of thing?
For sure. Like, technical writing was something that I didn't expect my career to go into, but like when I started doing open source stuff and really sort of doing developer relations and things like that, writing examples and documentation just really it's awesome. You get to learn something and then you get to explain it to somebody. And if you do it effectively, you can learn something and you can explain it to a lot of people.
Yeah.
So my approach with documentation is really to make something that people like to read. Because the rule of technical documentation is nobody reads. So, I want to I've always wanted to make documentation that people are excited to read. And I think back to video game manuals. Remember when video games had manuals that came with them? And, showing how old I am now. But you got a new video game, even if you knew how to play it already, even if it was Mario or something, you're like, I want to look at it. And like it had all these cool little illustrations in it of like what happens when you press the A button and Mario jumps, you know, like it had like maps in it and things like that. And you're like, oh, this is neat. Like even if you don't actually find it all that useful for the game, it's still neat to look at, right? It's like album artwork, you know, or the little booklet you get in the CD. It's like, I want to make things like that. Like I want technical documentation to feel like that when you read it. And so that's really where I get that, like my motivation, like how I want documentation to come across. And so for things like I wrote like a fantastic article. I say it's fantastic. Other people say it's fantastic as well. So I'm going to take their word for it. I'm not being completely full of myself here. I wrote an article about the way that the Roland Juno, which is an amazing synthesizer from the 80s, a trailblazing synthesizer from the 80s, how its oscillators work. It's like basically how the core of its voice works. And
I've actually got that here, so I'll just share that.
Oh yeah, please show it. Yeah.
So here's the top of the documentation. Is there anything in particular on the page that you want to show off or talk about? Where were you going with your?
Just start scrolling, buddy. So the thing is, like, you know, one thing that you'll notice here is like, you know, there's pictures, there's illustrations, like there's diagrams, like there's things that really help you pause and reflect and learn the information, but it's also nice to look at. And where I start really pulling in people and start really capturing your imagination and letting you not just read and learn, but interact is with this right here, what you're looking at, where you can actually change the parameters of the circuit and see what happens. So as I introduce each piece of the circuit, because I introduce them one by one by one, I give you the ability to mess with it, to experiment and see how it works and see how it responds to different things. So if you keep going, these sort of interactivities, they start getting gradually more involved and complex. And, you know, you actually get one where you can kind of make a sawtooth waveform if you're good enough. And you keep going and, you know, you start to get to ones where like you can figure out how a comparator works if you're giving it different voltages and like keep going. And like, you know, you start to see how, you know, an input voltage changes how the output looks. And, you know, some of these are simple. Some of these are literally just a slider that you get to pass back and forth. But having a chance to interact and actually see it with your eyes gives people so much of a deeper, more intuitive understanding of things. But it also just makes it a delight to read and play with. And, you know, I don't know. I think that this is a delightful way to present things to people, is
I think so often as well, a lot of these concepts are difficult to convey in words. And as soon as you get these sliders that you can grab and do things with, hope you're okay. As soon as you get the sliders you can grab, do things with it, it sort of opens it up to, oh, I understand now. It's like the picture says 1,000 words. A thing like this says 1 billion or whatever.
Yeah, and you know the thing is, like, what I also do when I'm documenting things like this is I try to put in the examples, the illustrations, and the interactivity that I would have wanted when I was learning about it. Because it's like you were just messing with the differentiator one, the one with the spikes, like figuring that out. like actually making that helped me understand how the differentiator worked. And actually, I made this before I designed the circuit for Castor and Pollux, which uses one of these, and it helped me actually figure out what that circuit should be.
Nice.
Like what the value should be in that circuit. And yeah, it's stuff like that. It's just like, I would have wanted this when I was learning about this. So, you know, part of this is like, you know, a letter to future me, where I'm like, this is how we learned this stuff. And this is how we understood it, you know? And yeah, and again, it comes back to like the game manuals and stuff like that. Like this is not as beautiful as an illustrated game manual, right? It's it's not album artwork where you're poring over all the lyrics as an emo teenager, right? But what it is some of that same essence
Yes.
in a piece of technical documentation, where it's like you're looking at your reading and you're like, I don't even care about synthesizers, but this is just so interesting to look at and play with. And that is my favorite kind of documentation. So that's what I try to make.
Thank you. Fantastic.
Yeah.
Well done, because all the words that I've seen you've written, they are so nicely presented and they make so much sense. And that's something that's really difficult. And targeting, the people that you are writing for is one thing, but making it accessible and things is a whole other thing. So well done. Yeah. Awesome.
Thank you so much. And it's I'm glad because I try.
Very good. Well, I think we're a little bit over time, so I won't keep you any longer. Thank you so much for joining us today.
Yeah, thank you.
It's been really good to talk and hear about all of your things going on. So yeah, thank you very much.
Absolutely. Thank you so much.
Next week, we'll be talking with Andrew Tierney aka Cybergibbons, about IoT and embedded security. But this week, that was Thea, and it's goodbye from us.